Hello, we have been discussing magnetism and what we have done so far is calculated the magnetic response of free moments which are just a magnetic moment J in in equilibrium with a finite at a finite temperature T, and that then we found out the such systems of independent magnetic moments in at a finite temperature. We found out the susceptibility of these, and that gave us the famous law of Curie, which is chi equal to n mu b square by kBT. Okay. For spin half system. So the interesting thing here is this dependence on temperature, which is 1 over T. Now, of course, people in the early 20th centuries were experimenting on several systems, and then what they found that this is a good theory for insulating systems, but when they studied metals, and their metals responded differently, and the susceptibility of metals was found to be independent of temperature. So, they behave like T to the power 0. So, that 1 by T is no longer seen in metals, the response of the conduction electron from the metals. Now, that immediately points out the fact that in metals electrons are they form a degenerate gas, and that there is a Fermi level, and that Fermi level severely restricts the phase space of the electrons. You cannot excite an electron inside the Fermi level. You cannot take an electron from the bottom of the pile to somewhere at the up, because all states up are filled up. You only can go above the Fermi level, and that means the fraction of electrons that can take any energy that you supply is less, is severely curtailed. Similar arguments we had used for specific heat. So, when we calculated the specific heat of degenerate Fermi gas and tried to find the linear temperature dependence of specific heat, we actually used the same concept. Now, that concept was also used here, and that calculation we will do. So, the problem that we are trying to solve is the observation that in metals the response of electrons gives a susceptibility in presence of a magnetic field, a susceptibility which is not 1 over T, not Curie's law. This is the celebrated Curie law, but it gives a very different behavior, which is T to the power 0. See, using Curie law, we actually used Curie law to get interesting physics, that the fact that Z was a function only of beta h, or h by kT, we used h by kT as the functional form of the Z, which is this h by T. This was used to find to show refrigeration. To actually, it was applied to refrigeration from few degrees to 100 or hundreds of degrees, but this was done using paramagnetic insulating materials, paramagnetic insulators, right. So, this is a very different thing now that we are studying. Here we are studying metals. and the response of metals is very different. And as I said, we will use the same concept that we used for a degenerate Fermi gas in calculating the specific heat. Remember, the specific heat also had a very different dependence from a constant in classical theory to a linear temperature dependence in metals, and that is similar argument we are going to do. What we will find out here is that instead of this 1 by T dependence, which the paramagnetic insulators indeed show, we have a T to the power 0 T independent behavior of chi. So let me just start the way we can find that. It's actually obtainable from a back of the envelope kind of argument. So let us just go back to that. So argument. So let me just go in at different levels. First, let's a very simple argument. Okay. So that is the physical way of understanding it. We have these levels which are they are all filled up. So all these levels are filled up by 2 electrons. So at any finite temperature, what is the fraction n that can take the energy from the temperature, which is kBT by EF, right? If kBT is a very small amount, it's very small compared to EF. Even at room temperature, it is nearly 1/100th of the Fermi energy, whereas this is the Fermi energy, and it is typically 2-3 electron volt, whereas at temperatures even at 100 degrees, you are nearly 100 factor of 100 down from EF. So this gives a reasonable estimate of the fraction of electrons that can take the energy. So these are the ones which can get excited above the Fermi level. So that is now that is allowed. Now again, let me use the Pauli Curie susceptibility form, the free electron susceptibilities, free moments. These are the electrons which can now freely interact with the field. So they can respond to the field, and so the chi will be this fraction n by EF into mu b square by kBT. Okay. So this will be the response of the. So instead of n, remember the n mu b square by kBT was the Curie susceptibility, right? What we have n mu square by kBT, and that n fraction is now not the entire set of moments. It's only a fraction which is kBT by EF. And if you just multiply this mu b square by kBT by n, you will get a mu b square by EF. So chi appears to be going like mu b square by EF. Now in 3 dimension, for example, the density of states is nearly flat at Fermi level. So you can approximate G of EF, the density of states, by 1 over EF, and then this becomes mu b square into G of EF. So that is a formula that of course it's not derived but argued physically, and it gives me a temperature independent. So this is temperature independent. So that is the argument that even Pauli, who solved this problem, he presented, and this is the argument that can be sharpened further. One can do a more sophisticated calculation, and one can find out that you get a very similar formula as it's just obtained here, and that's what let me show you one step. But before that, let me show you what is actually happening in the density of states. So the way the magnetic field interacts with the moment is basically mu b times h, right. So, this is the energy change, energy due to magnetic field due to magnetic field for an electron. Within a field H. So, the up electrons which are parallel to the magnetic field they gain an energy. So, their density of states comes down, they are just lowered, the energies are lowered. The down electrons which are misaligned with the field, their energies will go up, and so that is what is shown here. If you remember this figure, this is basically density of states versus E, but rotated 90 degree. We are familiar with this kind of a figure in 3D, for example, GE versus G of E versus E has a behavior which is like this, square root of E, remember, in 3D. So, that is the behavior that we are using here, and you just rotate it by 90 degree, then you will find this on the picture on the left. The other thing that has been done here is that normally we we do not distinguish between up and down spins. So, in this picture, up and down spins are have the same density of states, whereas here up and down spins are separated out, and so the way the picture is drawn is that this x axis is now on this side, E axis, and we have separated out G of E in two different G of E for up and G of E for down. The response of the screen is not good, but anyway, let us just rotate it. So, this will be my one sector which is up, this is my other sector which is down, and in presence of a field this up sector will come down in energy by mu b h by amount. So, this will be, their change will be minus mu b h for the up and mu b h for the down, okay. And that is exactly what is shown here. So, this is now the energy axis. There is nothing negative, remember the density of states cannot be negative, both sides are positive. This is also positive, that side is also positive. Okay, so what is shown here is exactly this thing, except that now you have a magnetic field. So, the magnetic field pushes the up sector down and the down sector up, that is it. Okay. The other interesting issue is what happens then. So, remember that you have a Fermi level. So, the Fermi level is somewhere here, which here translates to somewhere here, okay. So, this is my Fermi level. Now, if one sector comes down, the other sector goes up, then what happens to Fermi level? Well, it is interesting. This picture actually on the left shows you the Fermi level. If you had the Fermi level which is now different, for example, if up spin Fermi level, down spin Fermi level gets pushed up here, and the up spin Fermi level pushed down here, then there is excess electron here, and there are excess states here, and excess x number of states here, and so on. These electrons, the ones which are here, have a higher energy than these electrons, and then immediately what will happen is that the electrons with higher energy will just come to the other side and becomes then so if the Fermi surfaces Fermi levels had a mismatch, then basically electrons will get transferred from here to here, and then the Fermi level will again become the same. Otherwise, there will always be this transfer of electrons. So, Fermi level remains at the same. The system always keeps its Fermi level at the same place for up and down. Okay. So, in that case, that means there are certain number of electrons here. There are more number of states here, states that have that are accumulated here, and there is less number of states on the right hand side. Okay, and that is the that basically is the number difference of electrons between up and down. So, that is what one calculates by. You can easily calculate this number. What you can do is that you just remember G is not changing color. Yeah, now it will. So, let me wipe it and change the color. G of up at epsilon has now become the original G at epsilon plus delta half of that, because you are using half the densities are shared by up electrons, half down electrons, and they were equal when we had no field. Now, there is a field. So, this if you look at the picture, then see since the left hand part, the up spin density of states has come down. What was at originally at E plus delta E has now come down, and so that has become so you choose. So, let me just show you here. Suppose you had this density of states without field, and with field your density of states has become like this. Then what was originally here, suppose you are looking for at E. So, at a energy E, what was originally at E plus delta has now come down to E. So, that is exactly so the original density of states, which is at E plus delta, is now the density of states at E for up spin, and similarly it will be E minus delta E for the down spin. So, this we can just forget this. This argument is very simple, that since your density of states energies have come down, what was originally at E plus delta is now at E, and the original density of states is just G of E, and so it will be G of E plus delta. That is what we will use for G up. Similarly, G down of E will be half of G E minus delta. Here delta is mu B H, okay, because that is the shift that has happened. Okay. So, once you have that, then the rest of the calculation is straightforward. What you do is that you again now you again realize that the amount of the energy mu b h is much smaller than E f. Okay. So, this is a few degrees, as I said, even for a Tesla field less than a degree, and E f is some 5 electron volt, 3 electron volt, whatever. So, this the value that can be, this value can be approximated by the see the change. What you calculate is basically the change, right. So, that is exactly what is done here. So, look at the change. You need to calculate n up and n down, and their changes now. So, nu n up and nu n down after you put the field. So, what will that be, right? At the Fermi level, see, the changes are happening at the Fermi level. Now, you have extra states that came in at the Fermi level. So, what you can is that what you do is that at Fermi level you just approximate this g of up, for example, at E f. You can still approximate by g of E f original, okay, and g of down E f is approximated as by g of original g at E f. This right hand side is without the field. So, this approximation is fairly good, and just n up and n down is just multiply that by. So, n up is now g of half g of E f times this energy mu b h delta. So, that will give you the extra states that you have. So, the density of states times the energy window of energy, that is that extra window of energy that you have here, this extra window. So, that is the number, and similarly n down is the same number of states have crossed over to up from down into delta. Now, what you need is basically n up minus n down times mu b. So, m is mu b n up minus n down, okay. And this number is as you see is just the so m is mu b into delta into g of E f. The half and half will give you g of E f. So, that so remember the g this n down is a negative number, because n down has gone down. So, I could as well put a negative sign here. So, n down, this is change in a number, right. So, I can so nu n up is the original n plus this number, nu n down is original n plus this number, okay. So, that is the, so you can think of n up and n down as the increments in the number of particles in up and down. So, then their subtraction will give me a positive sign, and that's what I am getting here, and that gives me this mu b square into h into g of E f. Okay. So, this is what you get, and then chi is m by h equal to mu b square g of E f. It's the same thing that I got from a very basic physical argument of the counting the number of electrons fraction of electrons which can take the energy at the top of the Fermi level, at the Fermi level, the top of the pile. So it gives me back the same relation, and it again shows that this is temperature independent. You can actually go further forward, and you can calculate a more sophisticated way. There is there are ways to do it. So this is one, for example, which is more formal, but it just instead of just approximating the number by half of GEF into delta, instead we can do this integrals on the left hand side, and still I will show you that you can still get the same result. So this was our calculation 2. This is the approximate calculation number 2. So we can go further, as I show on the left, that we have this third, which is treatment, which is more sophisticated. Here again the same thing, but except that we are now doing in a more formal way. So again this half G of E plus mu BH times the Fermi function into d 0 to infinity. Okay. So this is n up, and similarly n down is half 0 to infinity integral G of E minus mu BH Fermi function dE. Okay. Which is what is done here. Now again we do the same thing, that mu B H is a very small number, so you can make a Taylor expansion. So how do you do? You just write E plus mu B H equal to, remember this half is, since n up density of states is half of G of original density of states without the field, that is what, because we have now separated it into up and down. So that half is still this half. This is no other origin, that we are just writing the density of states for the up and density of states for the down separately, as we did before. So this is G of E plus mu BH into G prime of E. Okay. And that is exactly what what has been done here. Now similarly, G of E minus mu BH is equal to G of E minus mu BH into G prime of E. Okay. So this is where we will start again, and we will continue here from here and do the integrals and show that you get the same result.